So for part 3 of Unit 8, vibration waves, what we've been doing is we've been talking about waves so far. And a quick recap of this entire thing is, well, wave is what? Wave was essentially a disturbance. And a disturbance is there because we've provided some energy to the system. And that energy is doing what? That energy has excited the particles of the system and they start to oscillate. And in doing so, what they're doing is they're transferring energy from one part to another, right? So what that means is that once you impart energy to it, the internal energy of this particles of the system increases, and that's what is causing that energy transfer, right? Because they have to come back to their equilibrium state, and that equilibrium state was whatever internal energy that the particle had before it was excited with energy or it was provided with energy, and it transfers on to it. Because what is the common thing with gases or solids or liquid? What's happening to the molecules in them? They're randomly colliding with each other, right? Solids, because they're attached or they're fixed, they're vibrating with the particles or their neighbors inside. With the air or with water, they're allowed to freely move. But there's still collisions happening, and in those collisions, that energy transfer occurs during that collision part, right? So wave was just that you provide them with some energy. That energy disturbs them, and that disturbance is what you observe in terms of an amplitude, right? And we've created that separate part of it, that it's a wave. And then what we talked about or what we talked about yesterday, is that waves could either be, a pulse type, which means that you only give them energy once, or a periodic type, so you're repeating that energy provision after a certain amount of time, and that time for a wave is known as its period, right? The amount of energy given is reflected in the wave's amplitude, right? And the wavelength is the distance covered by the wave during one full oscillation. One full oscillation's got what? It's got a crest and a trough, right? Now this could be represented by a sine wave or a cosine wave, depending on how we are trying to consider everything. Usually we start with a sine wave because it starts from a zero, so it starts from your equilibrium position and then oscillates, so on and so forth, right? The other stuff that we talked about is that waves, they only utilize the medium as a transportation of energy. They're not going to move due to the waves. So the perfect waves in this case, so when you're talking about sine waves, or when we're talking about transfers in longitudinal waves, not circular waves or all of those things, or what happens in between or due to combined motion of them, waves are doing what? They're essentially transferring energy, and they're utilizing the medium in doing so. So the particles would oscillate for that medium, and that would transfer the energy, and that's kind of it. Once that happens, or once the medium crosses or the medium density changes, you will observe something that's called a reflection. Now, there were two types of reflections that we talked about, and one was to do with open-end reflection and a fixed-end reflection. A fixed-end reflection would occur when the wave moves from a less dense medium to a higher density medium. For example, if you're talking near a corner of a wall, you will hear echo, and that echo is what? Your sound waves are hitting what? A higher density medium, which is a wall, right? And they're reflected off of it. When they're reflecting off of it, what's happening is that you're getting, or they're moving back in a separate phase. So part of that energy transfers off to the higher density medium, part of that energy is reflected back, and that's known as a fixed end reflection. For an open end reflection, it's moving, or the wave's moving from a higher density to a lower density medium. So for example, your light waves moving from water to the air, and that's why you see that bend. And we'll talk more about why the light waves bend or not. That's due to rarefaction, but that's for Monday and Tuesday perhaps. But more importantly, there's a reflection that's going on. The important things to note here is that when you've got a fixed center reflection, the phase changes, or the crest of the wave upon reflection changes into a trough of the wave. When we're talking about open-end reflection, what happens is that the reflection still occurs, but your phase isn't changing, or the reflection would, your crest would still remain a crest, right? And remember, energy still, because energy is conserved, upon reflection, what will happen? Part of that wave will lose its amplitude, and that loss in amplitude will go where? It will go on to move through the higher density medium or the lower density medium, and the reflected wave would have a smaller amplitude, right? That's because energy transfer occurred. The other thing that we talked about is, well, we're going to have a standing wave, and before that standing wave, we talked about, well, what is an interference? Interference is when two waves moving at different speeds will overlap each other, and due to superposition, right, their amplitudes may cancel out, or they may add up, and that's known as either a destructive interference or a constructive interference. A destructive interference is when your amplitudes would cancel out. A constructive interference would occur when your amplitudes will add up, right? And a standing wave has both of these things happening. You've got constructive interference and you've got destructive interference. Right? Yes or no? Okay, I've got a few yeses. And then standing wave was essentially, well, you've got reflection, and that reflection overlaps with the traveling wave, and that creates, although the waves are still traveling and reflecting and bouncing off of the clamped ends, what is essentially happening is, because they're in sync with each other, the crest and the trough either matches up, and that creates a destructive interference, or the crest will match up with the crest of the reflected wave, and that would create a higher amplitude or a constructive interference. And the particles of the wave would be oscillating about their equilibrium position. So when we're talking about the string here, the string would be, here you can see in this little simulation or animation, that the red and blue waves are traveling. Once their crests overlap with each other, you get a higher amplitude or an antinode created, and once they're out of sync and the crest aligns with the trough, what is happening is that you get a destructive interference, and the string seems to be at its equilibrium position, right? And the red dots there in this video or in this animation are showing you what are they showing to you? Are those the nodes or the antinodes? You could use the chat menu too, so if you know the answer. What are the red dots? Nodes. Thank you, Natalie. So the red dots, they are kind of locked into the position, so they're kind of the anchor points within the standing wave for that string, right? And a few of the wavelengths that we talked about, and this was the answer to question 4, is that by clamping the ends of the string, you could create a standing wave, and one way to do it was to create half a wave or a full wave within a string, or a combination of those things. But the important part is that you have to have nodes on the ends of the string in order to create a standing wave, right? And then moving on, we talked about pulse and periodic waves and all those things. The next thing is, well, it needs source. So more importantly, the source could be, well, point type source. So you've got one source from where the waves are kind of emanating or pulsating from that location. So sound wave acts like this, or you could have a planar type wave where you've got something to do with the plane that will come and disturb the medium, and that would create waves. So think about ocean waves are more of your planar type disturbances because they're kind of moving in a straight line, right? But the next part that is kind of important is to talk about diffraction. Diffraction is what? Diffraction is where these waves that are originating, when they come in to a proximity of an opening or a gap, they would bend around corners. It's easier to see within a sound wave. It's easier to see within those artificial shorelines that you see that have been created for boats to come in and dock. So they're kind of stationed away, or they're stored away from the harshness of the sea waves. And that artificial shoreline or rock line is that something done to create this artificial barrier, so the full power of the waves is not transferred onto the boats themselves. And that's one way to do it, and they're using the principle of diffraction to do it. We're not going to go into diffraction patterns or whatnot, but essentially remember, when you've got multiple slits within a wall, that would allow multiple waves to pass through, and those multiple waves would then interfere, and that would create diffraction patterns. Right? Any questions so far? If not, let's start with sound waves. Sound waves are what? Sound waves are longitudinal waves. What do longitudinal waves do? Or what were longitudinal waves? Longitudinal waves are waves in which particles are moving in parallel or oscillating in parallel to the direction of wave motion, right? And the way that they're doing is that they're creating, or they're doing it in a series of compressions and rarefactions, right? Or a series of compressions and expansions. So think about this. Think about, do this with me. Hold out your hand in front of your mouth and then talk. Say something, anything. Do you experience anything when you're holding out your hand in front of your mouth when you're talking? Do you feel something on the palm of your hand? What is that? That's a sound wave. That's your disturbance, right? And what that means is when you're talking, the air particles are pushed together and they create this compression zone, or that pressure zone. That's what you experience on your hand. So what happens is, once you're talking, once the air particles have been compressed, they've been pushed to one end. Once that happens, once the air particles are pushed, there's a gap. That's where there's a vacuum that's been created by the particles that have been left. And that's where that expansion zone comes in, or that's what's known as a rarefaction, right? So these zones that you see right here, where you've got these concentrated particles, this is a compression, and that's where the crest of the wave lies in the sound wave. And then where this expanded or less particles are seen, this is a rarefaction, and that's where the trough of the wave lies. And this is one of the reasons that sound waves are also known as pressure waves. That what you experienced on your hand when you were talking, it's a pressure wave. That it created some pressure, and pressure is directly related to the force. And we haven't done fluids, but essentially the pressure is creating or exerting a force on you, because and once we come back, please remind me, and we'll go over fluids slightly, how pressure exerts, or how force is exerted due to pressure, right? So sound waves, many things can happen, you've got loudness scale, and you've got the intensity scale, and you've got the frequency scale, but more importantly, humans can only hear what? They can hear between 20 hertz and 20 kilohertz. And hertz is what? It's the frequency or the change in, or how many wavelengths are available within a given second, or how many waves have passed through it within a given second, right? Depending on the period of the wave. So humans can only hear between 20 hertz and 20 kilohertz. Anything beyond 20 hertz is your infrasonic region. Anything beyond 20 kilohertz is your ultrasonic region or ultrasound region, and that's where your ultrasound term comes in, and it's got a lot of medical benefits, right? When it says, so if you kind of see here that medical and destructive, why would you call it destructive? Any idea? Remember, what are waves again? Waves are disturbances, and they're essentially modes of energy transfer. So when we're talking about that a wave could be destructive in nature, that's what tsunamis are, right? So ultrasonic waves are going to be what? They're going to be, or they're used medically to get rid of stones within your body, so kidney stones and all of those things. That's where ultrasound or ultrasonic waves come in, right? So they keep on impacting if you've got kidney stones, or if you've got what are some of the other stones, gallbladder stones and all those things. What is happening there is that if you keep on impacting those stones, you're essentially transferring energy to them, and that energy is going to cause them to break into pieces, because there's a certain limit to what the stones can take or withhold. But more importantly, you've got sound that is being divided into these bands. Humans can only hear up to acoustic, or this level between 20 hertz and 20 kilohertz. And we'll talk a bit more about loudness scale and decibel scales, but this is the audible range for humans. Apart from this, it's kind of below 0 decibels, you can't really hear anything. Then when it gets to above 150 decibels, it kind of becomes too loud to bear, right? And that's just a generalized scale of what's going on. But more importantly, what sound waves are, remember we talked about that sound waves are traveling longitudinally, right? And what are longitudinal waves? Longitudinal waves are when the sound waves or the particles of the waves are oscillating back and forth or along the motion of the wave, right? But when you start thinking about in terms of the three-dimensionality of the wave or the sound wave, what happens is that these waves would travel in a spherical format, right? So in one dimension we had the waves traveling in a back and forth pattern along its equilibrium point. Once we go into the 2D part, it's going to expand, or it's going to emanate like in a circular format as the one that you see in the image in front of you. Now expand that into a 3D part or a 3D visualization, and that would create a sphere, right? With the source at the center of that sphere, right? But more importantly, you've got the wave that is going to travel equal amount of distances within the given zone, and that is known as your wavelength. The compression zones are usually shown to you in terms of these wave fronts. These wave fronts are given to you in terms of the gray lines that you see here. Again, this chapter is more to do with the concepts part. There are less equations in here. The only equations that you've seen so far is to do with the frequency of the wave and the amplitude of the speed of the wave, and that's it. Everything is all kind of given to you, or you could read from a graph based on what type of a wave it is, right? Once you transfer this off to, well, now consider this, what is happening is, or what was happening in this last picture, is that the sound waves are traveling, and they're traveling at an equal distance from the, or they're covering equal distance in a given amount of time, right? Now what happens when this source starts to move? When the source starts to move, what will happen is, in one direction, it's going to create a relative velocity between these sound waves, or these wave fronts. When this relative velocity starts to happen, what you observe is that on one end, or in the direction where the source is moving, the sound waves are starting to collect or coalesce, right? And once they're starting to collect, the distance between individual waves is going to start to decrease, as you see right here. So once this starts to move, the sound wave, or the wavelength between these two wave fronts, is much less compared to the ones that are behind the moving object, right, or in the opposing direction. And what this creates is, this creates an artificial sense of a smaller frequency in the direction where the source is moving into, right? So that increases your, or that reduces your frequency, sorry, that reduces your wavelength, but it increases your frequency, that the person, if the person was standing in the direction of the moving, in the direction where the source was moving, that frequency would increase. That means that you're hearing the sound over and over again, and that increases the pitch. So pitch and frequency of a sound are interrelated. So the higher the frequency is, the higher the pitch is usually going to be. And on the opposite end, what's happening is, because the distance is increasing, because the source is moving away from that direction, the wavelengths are increasing. That means that the sound is taking a lot longer to reach that point, and thus you get this artificial sense that the frequency of the sound is decreasing, right? And that's what you see, or that's what you observe in your safety cars, right? So when you've got an ambulance or a police car blowing its siren out, if you're standing in its path, you're going to hear a really high-pitched sound. That's why it becomes really uncomfortable when the car moves through. But once it has moved through, what happens? You don't hear the siren as much. And that's this artificial sense of, well, what's happening to the frequency, or this artificial frequency that has been created due to the source that has been moving. So in the direction of movement, the frequency is going to increase. That creates a higher pitch. And the opposite direction, the frequency is, or this artificial sense of frequency means that the frequency is reducing. The frequency of the sound wave is a constant though. And this entire phenomena is known as the Doppler effect, this artificial frequency creation, right? Does that make sense? Does that make sense? Okay. Now there are two important rules. Where is that slide gone? Okay, there they are, right up the top. The two important rules are that the speed of the wave is a constant within a medium, and the frequency of a wave does not change upon reflection. So these are really two really important parts when it comes to wave features or rules regarding waves. Now, given that, we can kind of come to the point where we can talk about the intensity of a wave. Intensity is what? An intensity is basically the rate of power delivery per unit area of the wave. So what that means is, or that could be written as, is that, remember, power is what? It's the rate of change of energy. So the E over delta T part, that's where this power comes in. And this is the area part. So how much energy could you deliver per unit area of the wave? And that, what that essentially means is that it's measured in watts per meter square. And what this also means is that the closer you are to the source, remember, what are sound waves? Sound waves are longitudinal waves. When you start to think about sound waves in a 3D sense, what are they creating? They're creating a sphere around us, right? And that spherical area, the wavefronts are going to be covering a spherical area. That spherical area is given as, or the area of a sphere as 4 pi r squared. So the further out you're moving, the energy transfer that occurred during the sound wave, that's going to remain the same, right? So your power delivery or the energy carried by that wavefront is the same, but it's more spread out. So the further you're moving out, the larger that spherical area is becoming. And since the larger that area is, that energy is distributed along that spherical area where the wavefront is. So the closer you are to the source, the more intense the wave is. The further out you move, the less intense the wave is, right? And that's all because to do with how much energy or the energy spread out over the area, right? And that's why you kind of don't hear people on longer distances, right? Or you have to shout, or you have to, and shout is doing what? It's increasing the energy delivery to the wave, and that's what loudness is. Loudness is your amplitude of the wave, and the higher the amplitude of a wave, the more energy you've transferred to the wave, right? Questions with this? No? I've got one question, and I believe you should be able to solve it, but essentially what you have to do, let me quickly try to do it here, but do you have a minute? Because it won't take more than a minute. Let me share my Jamboard with you. Let's go here, let's open the Jamboard, and let's do a window. So the question was stating that you've got, well, the intensity, what is the intensity of a sound wave produced by a trumpet at a distance of 3.2 meters when the power output of the trumpet is 0.2 watts, right? So we're trying to find intensity. Remember, what is intensity again? Intensity is the power delivery per unit area, right? And area, because sound waves travel in a three-dimensional form, they create a sphere, and the area of a sphere is given as 4 pi r squared. So intensity is quite simply power divided by 4 pi r squared. Now the power has been given to you at 0.2 watts. We've got 4 pi, and then the radius or the distance was what? 3.2 meters. And we square that, and the answer is going to be 4 pi 3.2 equals to 1.55 into 10 raised to the power negative 3 watt per meter square. Right? Now, I believe that's all the time we have today. So when we come back,